我们来看一下这个电流在一个导线里头的流的状况。For DC current and for AC current, the behavior are different. Well, for this configuration, you have a DC voltage applied to a piezo conductor. And you know that there will be a current generated inside. And from this geometry, there's no reason that there will be more current here than here. Across this cross-sectional area, the current is going to be uniform. Right? 因为在这个导体里头呢，没有道理说这里的电流比这里要多一些。So you have a uniform current going through a piezo conductor, provided you have a DC driving power supply. 所以这个图没有问题。But the situation is different. If you have an AC driver, if you have a DC. 谢谢。我们来看一下 if you have an AC power supply, for example, if you have a harmonic oscillation of the current inside this wire, and then you try to locate the current in this piece of copper, for example, then the distribution of the current is quite different from the distribution of current for this case. To understand this, let's look at this geometry. Well, think about you have an electromagnetic wave instant on this piece of metal. And then in the last 1 hour time, you understand that the electric field and magnetic field will attenuate along this direction with a skin depth sigma. For this case, you have electromagnetic wave going this direction, and then when this electric field and magnetic field instant on this piece of conductor, there's a penetration of the field with a distance of sigma equal to 1 over square root pi f mu sigma, or delta equal to this. Right? And on this piece of conductor, you have electric field and magnetic field on the surface. And this current is going to be, you have a surface current on this piece of conductor. That is equal to AN2 cross with H, if you still remember. So you have this kind of surface current on the surface of this conductor. That is equal to the magnitude of this H field. Suppose H is along y direction. This is along z direction. Okay, this is along x direction. So if I have H on the surface, that is y component, then I have Js equal to Hy, but the whole thing is going to move along x direction. Okay. 这个 surface current 是 per unit length， 在这个y 的方向上头每单位长度的电流密度。Okay. 所以呢，你如果有一个 AC 的场打到一个导体上头的话，这个电流呢会在这个方向越来越小，越来越小，越来越小。 Okay, now think about this reverse situation. You have some AC power supply driving this current, and this piece of conductor is going to radiate like a antenna， 像一个这个天线一样产生辐射。所以呢，这个是波打进来，这个是波离开。那在这个观念上头，只是把时间反过来，所以基本的物理没有反过来。Only the reverse of time. So this means that the surface current, the current inside this piece of conductor is going to be on the surface of this piece of conductor. OK， 这里是波打过来，这是波辐射出去。在这整个观念上头呢，是时间上头的翻过来，物理并不变化。OK。Now, this is the simplest way to describe how the surface current is created on a piece of conductor due to an AC power supply. Okay. Now, rigorously, in fact, you can solve for the wave propagation inside a piece of conductor, a piece of wire, but that is too much complicated. I'm not going to do this derivation, but in fact, 你的助教最近有算过一次，就是一个这个 wire， 它的电流、它的场都会在这个表面上头。Okay, if you are interested, you can consult your teaching assistant. But the derivation appears to be quite complicated. But this is the simplest explanation for the surface current induced on a piece of conductor due to an AC power supply. So previously we have a definition of E over H, that is called wave impedance. We can also define a surface impedance for an electromagnetic wave instant on a piece of conductor. Okay, so now we have this E over H definition for this wave impedance. Well, the same thing, you can define this Ex over Hy on this surface. Okay, Ex over Hy, 这是 x 方向的 electric field, 这是 h 方向上头的 h field. Ex over Hy, we define it to be surface impedance of this wave, when this wave just instant on this piece of conductor. But this Js has been calculated to be equal to Hy, so this surface impedance is also equal to Ex over Js. Okay, and this basically is a expression equal to eta c. So eta c is the surface impedance of a piece of metal. Okay, and later on I'm going to introduce you the Poynting vector, the energy flow, and the loss inside this piece of conductor, and then we'll come back to pick up this Rs for calculation. Okay, but now remember that this eta c in fact is equal to this surface impedance, and there's a real part associated with it and imaginary part associated with it. Okay. 好，我们来看下一个很重要的 topic， 叫做good velocity. We talk about harmonic wave, harmonic field that propagate with sinusoidal variation in space and in time, and but very often that everything has a starting point and has an ending point. 在人的这个世界里头呢，什么东西都有开始有结束，不会永远就是有一个这个 harmonic oscillate 在那里动的这个永远没有开始或者结束 ，right? So if you have something, if you have a starting point and if you have an ending point, then we can measure the speed of the energy. And turn out that the speed of energy is different from the phase velocity. Okay, for whatever anything that has a starting point and ending point. The important thing is the whole thing, the propagation speed of the whole thing, not a certain point inside the sinusoidal variation. 譬如说，我现在如果有一个打出一个脉冲出来 ，What I care is the speed of the whole group reaching me. 如果说这个是高能雷射的话，高能量的激光、高能量的雷射的话，the receiving time is the time for the whole group to reach me, but not quite the individual field point. Okay, and the individual point on this phase is called phase velocity, and the speed of this envelope is called group velocity, and these two velocity could be different. Okay, 那你可以看得出来 the energy velocity is the group velocity, not quite the phase velocity. That is different. Okay, just like if I throw you a piece of chalk, the energy velocity is going to coincide with the body of this chalk. Okay, we don't quite care about the details of the wave inside this envelope. 所以呢，这个 group velocity 跟 phase velocity 是不一样的。All right. 所以呢 this group velocity, I have described the concept of it, and this group velocity is the velocity of energy. And that's why this group velocity is important, because the energy is money, right? So if you have something, if you have a starting point and ending point, it's not going to be a harmonic wave anymore. It requires more frequency component to synthesize this kind of electromagnetic pulse. 它不再是单频的，单频的波的话呢，它是上上下下，然后无止境。但是呢，你有什么东西有开始有结束的话，它一定是有其他不同频率在里头。Okay, so suppose that let's pick up two frequency component, two harmonic wave like this and this wave, and they are different by some frequency. 2 theta omega is a frequency difference between these two fields, and then you sum them together. With this sum, you can convert this summation into multiplication. 这时候呢，你会发现，这个是高频的部分，这个呢 theta omega usually is low frequency. Suppose this theta omega is very small compared with omega. Okay, so you have two terms multiplying together. So you have like a phase oscillating, well, you have phase oscillating term, and then multiply with a slow term. These two terms multiply together. The frequency associated with this is theta omega, and the frequency associated with this is omega. And then you multiply them together. Once you multiply them together, you end up having this kind of wave. And you have an envelope outside this phase oscillating field. 那在这里呢，我们说能量的传播跟这个波包有关系。这个波包呢，有一个传播速度。在这里头，波包里头这些 phase oscillating field is going to go with this omega minus beta z term. So there's a phase velocity associated with this phase oscillating components. Okay, so there's a phase velocity equal to omega over beta for this phase oscillating field. But for this envelope, that is described by this term, also has a velocity called group velocity. Okay, equal to theta omega over theta beta. if you have a continuous distribution of the frequency components, and you sum them together to have a pulse like this, then this definition of this groove velocity becomes d omega over d beta. For the two frequency components, it's easier for you to see how this envelope propagates. And with the different velocity from the phase velocity of this phase oscillating components. OK， 有没有问题？那这里有一个 animation， 你可以看到就是里头的这个场呢是变化，跑的时候跟这个 envelope 的这个速度是不一样的，所以你会看到里头这个 envelope 里头场的是在变的。OK，let's see an animation. Okay, you see envelope associated with this, and you see this field, in fact, going up and down relative to this envelope. It's going up and down. This means that the envelope propagates at different speed of this field patterns. Okay. 如果说这个 envelope 跟里头的 field pattern 跑的速度一样的话，这里头不会上上下下在动。Okay. Because the envelope propagates at different speed with respect to this oscillation. Therefore, you see this oscillation change the amplitude inside the envelope. 如果说这个波包跑的速度跟这个field 的 pattern 这个里头这个 phase oscillation component 跑的速度一样的话，那里头的这个样子不会变。OK， 有没有问题 ？If this phase velocity is equal to this groove velocity, then the pattern does not change inside the envelope because they co-move together with the same speed. Okay, but if the phase velocity of those field is different from the groove velocity, the envelope velocity, then you're going to see that the amplitude move up and down inside this envelope. And that's why we have this animation. OK， 这是为什么你会看到在这里呢？你会看到这个里头呢，在波包里头这个场呢上上下下在动，因为两个速度不一样。OK， but what we care is this envelope velocity, because this envelope carried the energy, and we call this groove velocity. Through this animation, I think it's quite clear to you that the groove velocity is very important, okay, and it's not necessarily the same as the phase velocity given a signal. 了解哈 ，OK。所以这是 groove velocity 的这个概念。So from here on, you have to remember that because this expression is quite simple, you have to memorize it. You have to remember it. Okay, this is omega over beta. This is d omega over d beta, and d omega over d beta defines the speed of this envelope. Okay, but in fact, these two are related. Well, apparently you can derive one quantity from the other. Your phase velocity is equal to omega over beta. So if you have, say, beta equal to omega over up, and you do, you said that sometimes this omega beta diagram is nonlinear. Okay, so sometimes this beta is a function of omega. So you can do d beta over d omega. This is 1 over u groove velocity, all right, if you just look at this expression. And then on the right-hand side, you have 1 over beta. No, you have 1 over UP. You have 1 over UP minus omega UP square DUP d omega. We can do a differentiation. Therefore, you start to relate your group velocity to your phase velocity. Okay, so you can continue to organize it to UG, the group velocity, equal to the inverse of this. So you have say UP 1 minus omega UP DUP d omega. So if you know the phase velocity, and if you have this omega beta diagram, so you have the information of DUP over d omega, then you can calculate UG, the group velocity. Okay. In the case that you have a linear curve, this differentiation is equal to 0. So UP equal to UG. So in some system, if I have a nonlinear curve in the omega beta diagram, then the group velocity and phase velocity will be different. And we call this if DUP over d omega not equal to 0, then we call this system dispersive. 这个系统如果有 dispersion 的话呢，也就是它的反应跟频率有关系，速度跟频率有关系的话，我们说这个系统是有 dispersion。OK， 好，所以这是我们刚刚算出来的一个结果。我们来看一下哈，这个 dispersion 呢有几个 category。When this DUP phase velocity is a function of omega, or this beta is a function of omega, this means that the propagation speed is now also a function of omega. Okay, and your UG is also a function of frequency. So this means that the different frequency component can move at different speed in this system. 那你如果你们都看过彩虹 ，if I have a prism, and then you send a white line through this prism, you're going to decompose it into different colors. All of you have seen this before, right? If you put a prism into a white light, then you can disperse the white light into different colors. This means that the blue light is going to bend more than the red light. 那这个呢是因为它折射率比较大，所以它像素度比较慢。所以在这个状况之下的话，是 blue light propagate slower than red light. Okay. For this case, blue light propagate slower than red light. 所以呢，它被偏折的角度比较大。So in a piece of glass, different frequency component can propagate with different speeds. 那这个状况呢，因为我们经常看到 ，so we call this normal dispersion. So if this material has no dispersion, I just mentioned that if you have a linear curve in the omega beta diagram, then your UP equal to UG, and this system has no dispersion. Okay, but if your DUP d omega is less than 0， 就是你频率越来越高，你的像素度越来越低。你这里会小于0，这里小于0的话，这里小于0，所以 you have a in general groove velocity less than phase velocity. OK， 频率越来越高，速度越来越低。Blue light has a higher frequency than red light. 这是短波长，这是长波长，所以频率变高，它速度变慢。We call this normal dispersion. Okay, but if you have some materials that give a higher speed, a larger speed for high frequency components, then we call it anomalous dispersion. That mathematically tells you that the differentiation of the phase velocity with respect to frequency is larger than 0. This expression tells you that the phase velocity will increase with frequency. OK， 这个现象呢不常见，所以我们把它叫做 anomalous dispersion. So for different materials, it could be zero dispersion, it could be normal dispersion, it could be anomalous dispersion. For the zero dispersion, it often occurs at one frequency point, one wavelength. 在某些这个波长的时候呢，有些东西是没有 dispersion 的，但是呢，几乎我知道没有任何物质呢是 broadband 都没有 dispersion. Okay, so this is one expression that describes the groove velocity in terms of phase velocity with differentiation of the phase velocity with respect to frequency. But don't forget that your U, P, also equal to frequency multiplied with wavelength. 所以呢，你这 differentiation with respect to frequency can be written into a differentiation with respect to wavelength. 这里呢必须要改写。OK， 那你们课本里头后头有一个习题，就是把这个式子改写成对波长的微分，你自己练习一下。OK, any question? 所以这个观念是 groove velocity 跟 phase velocity. And remember that the groove velocity means the velocity of the energy. Okay. There could be some exceptions. 当你在这个系统里头，我们刚刚说 groove velocity is the speed of the energy. But there could be some exceptions. All right. Later, if you spend a little bit more time on electromagnetics, you'll find that there could be some exceptions. 那通常这个例外的状况呢，是在这个系统里头，这个波的能量很难去定义的时候呢，会出现例外的状况。OK， 譬如说 ，if you have very lossy system， 在一个非常损耗非常大的系统里头，它能量很难去定义。这时候呢 ，groove velocity 不见得是这个能量的速度。OK， 那这是例外，稍微提一下让你了解到这个书里头给你的不见得是永远都是正确。You have to think about it. OK. Okay. The next topic is also quite important. Whenever you deal with the calculation of energy, power, it's very much important because a lot of human conflict comes from the struggle for energy and power, right? So there's a way to calculate the power for electromagnetic wave. 你把这一项做一个 dot product， 做一个这个 divergence。E cross H, and then use this vector identity, you can come up with these three terms. 有三项在那个地方，这三项呢在右手边 you can recognize from your previous knowledge. this on the right hand side, this become the differentiation of mu h over time, mu h square over time. 那之前的话你学过。If you still remember, you have a piece of conductor. You have current inside. And then the power inside this piece of conductor running a current is equal to Ga dot E integrate over the volume. And this is called Joule's law. So somehow this is related to the power density. And previously, you also calculate the energy stored inside a piece of capacitor, for example. And the energy is equal to 1/2 E dot D, and then integrate over some volume. This can be written into 1/2 epsilon E square dV. This is associated with the electric energy. And you also calculated the magnetic energy stored inside a piece of inductor. That is equal to 1/2 B dot H and integrate over some volume. Okay, and this can be written into a pure scalar form, H square mu dV. So when you look at this expression on the right hand side, this E dot J similar to the same as this. So you understand that this E dot J is a power dissipated inside a piece of conductor, ohmic material. And this can be written into sigma E square integrate over volume. So you end up having this sigma E square. And this first term basically is the same as this term differentiated with respect to time. 所以呢，这个能量对时间微分之后，你就得到 power. Okay, so somehow this is power, this is power, this is power, but that is normalized to the per unit volume. So this is power density. This is power density. This is power density. Except that this power density is associated with ohmic loss. This power density is associated with the electric energy. This power density is associated with the magnetic energy. Okay, so with this interpretation, now you understand that this is a power density associated with the electromagnetic wave. Okay, 我们现在呢放一个 divergence theorem 上去 ，apply divergence theorem, and then on the right hand side you have all the integrations over volume. And then on the left-hand side, you have an integration over surface. So think about some geometry. Think about some geometry. There's a surface bounded volume, and then you have radiation. If we just do a surface integration, then you can collect the radiation going out or coming in. Okay, if you have a radiation either going out or coming in, the time change of the electromagnetic energy inside this volume is going to change with time. 所以左手边等于是你的 radiation energy 出去或进来的量，会等于里头的电磁场的能量随时间的变化，再加上一个这个在里头的ohmic loss. So this is an energy conservation. Okay, so think about this. This is an energy conservation. If I have 因为这是 surface outward, right? 所以这代表说 你辐射出去的能量会等于这里头储存能量对时间变化的这个复数，减少的能量，这个里头减少的能量。总共减少能量呢，除了这个里头储存的能量的变化之外，还要包含一个项，这一项呢是 ohmic loss 在里头。So this is energy conservation. Okay, whenever you see an equation, you have to interpret the physical meaning of it. 那这个负号，因为这个 ds 的方向都是朝外，所以你在计算的是朝外辐射出去的能量有多大。Is equal to the decrease of the internal energy plus the consumption of the energy inside the material. Okay, so this is a very important calculation, E cross H. It also tells you the direction of this energy flow. So this is called Poynting Vector. 在这里有问题？对这个式子的物理意义。Okay, so Poynting Vector is written into E cross H because the surface integration gives you the power, time change of the energy according to this equation. So this is a power. So this has a unit of watt per square meter, the power density. Okay, 所以这在光学里头呢，这叫 intensity。它的这个单位是 watt per square meter in MKS unit. So suppose that I have a wave, electromagnetic wave like this, and I want to do a calculation for the Poynting vector. In phasor notation, I'm going to have a phase like this in this phasor notation. 在你注意，你讲义里头跟这个投影片上头呢，旧的投影片上头这里有错，你要注意一下。Okay. 那 if I want to calculate the instantaneous Poynting vector, basically I do this cross product. Okay, I do this cross product, and then I have this term multiplied with this term, with phi e and phi h. 我在这里好像在这里吧，这个好像在讲义上是写成 phi， 你要改一下。Okay, so this is the instantaneous 即时的这个Poynting vector, 你的 power density, and this multiplication can be decomposed into two terms summed together. One is a function of time, and one is nothing to do with time. So this power oscillates up and down. Okay, for this term, I give you some energy, but I'm going to take it back in the next cycle of time. So for this term, 我们两相无欠, right? I give it to you and take it back, give it to you and take it back. So actually I don't care about this term. What I care is this term. Either I give you the energy or I take energy from you. So what you care, in fact, is the time average part of this expression. What I need to know is this term. For this term, I don't need to know the details because I give energy to you and then you give it back to me in the next cycle. I just want to know what I permanently give it to you or what I permanently take it from you. OK, 所以这一项很重要。这一项很重要呢，这是平均的这个能量。So if you average it over a long time, this is the only term you care about. Okay, so this is the only term you care about. And 这一项怎么计算 ？We talked about it a long time ago when I talk about the IV, the power equal to I multiplied with V, but the average of it, the average of this power is equal to 1/2 real power I V conjugate. Right? The same thing for this Poynting vector, the average power density is equal to real part E multiplied with H conjugate and divided by 2. 这一项可以从这个计算里头得到出来。 and this is the same as the calculation you use for your circuit. OK， 那跟这个 IV 不一样的是什么呢 ？Electric field and magnetic field has a direction. So this Poynting vector, this power density, has a direction. Okay, so we somehow has to do this calculation, this complex Poynting vector, that is equal to the phasor of E cross product with phasor of H conjugate divided by 2, and take a real product of it. You have an average power density going along some direction. And you also give you the information of the magnitudes. 所以呢，这里有方向，还有这个大小的讯息在里头。Okay, any question? 最后我们来看一下，我们来算一下这个能量在这个导体里头的损耗是怎么样。Okay, now you have a surface current. Okay, you have a surface current. Therefore, you have some loss inside this material when you send electromagnetic wave into this piece of conductor. And so the complex Poynting vector is going to be equal to Ex cross with Hy along this direction. Okay, but your Hy in the last part of my lecture, your Hy is equal to surface current Js. So this can be written into if you still remember, this is the Ex Hy is equal to eta C, and it's written into Zs surface impedance, and it's equal to Rs plus J Xs, right? So if you do a Ex cross with Hy, take 1/2 and take real product of it, you only keep this term. Okay, you only keep this term, so you end up having this expression, and you have Hy equal to Js. So you end up having this term right here. So this is the complex point, the real part of your complex Poynting vector. That is the power density in this area. But if you want to calculate the total power loss, you have to integrate over the surface. The surface is theta x theta y, give you an area of AXY. OK, 这 AXY 呢就是把这个乘上去，这时候呢 you get the total power dissipated on this surface. 那这个这一项呢 ，Js 是这里的电流 per unit length over delta y. So if you multiply Js with delta y, you get the current, surface current. OK, 所以呢，你可以把这一项乘上 delta y 的平方，再除以 delta y， 你得到这一项，了解吗？Your P is equal to S multiplied with delta x delta y is equal to 1/2 Js square Rs delta x delta y, but now you write delta y squared divided by delta y. And then you group this term and this term together to get Is squared. So you have 1/2 Is squared Rs delta x delta y right here. Okay, and you know what Rs is, because Rs basically is the real part of this eta C. Eta C 之前我们不是算出来是等于 1 plus J alpha over sigma, right? Is this. 所以这上头这个波打上来之后，它消耗多少能量在里头，你可以算出来。Okay, if you are confused with this surface resistance, or sometimes myself also confused with this surface resistance, surface impedance, then let me tell you a simple way to understand this. Well, you are familiar with R equal to L over A sigma. 这个不在你课本里头。OK， 你知道这个 R 是 L over A sigma， 然后呢，你又知道这个 power 可以这么计算，1/2 I 平方乘以 R。OK， then let's look at this L. L is from here to here, delta x. A is the area. Area is the delta y multiplied with a characteristic depth in this direction. Right， 一个这个导体它的这个有电流这样子流，然后呢，它的 cross section area is going to be equal to delta y multiplied with the depth of this current, and the depth of this current is equal to the skin depth. So delta y multiplied with delta, the skin depth, and then conductivity. So you end up having R equal to this. And then you calculate the 1/2 I squared R, put this R into this expression, you end up having the same expression. So this is consistent with your circuit theory. Okay, so this is sort of a way, sort of to borrow the circuit theory to understand this power loss on the surface of a piece of conductor. OK， 有没有问题 ？Yeah。因为你的电流，你有 loss 的地方，就是你有电流的地方而已。那在这里呢，这个你假设这个电流主要都是在这个不是假设，你的电流就是在它表面而已。你说这个分布下来，对，但是呢，这个分布下来呢，是你都已经把它积分上去了。当你算这个 surface current 的时候呢，你看啊，这里有一个这个 trick 是，当你算这个 surface current 的时候呢，你做这么一个动作，那做这么一个动作的时候呢，是假设说你的这个是电流是这个方向每单位长度 delta y 每单位长度的电流，所以呢，把底下的这个电流全部都是放上去了。This is a surface current per unit length over delta y。所以呢，这底下的所有电流呢，其实都加上去了。Okay. In other words, we are doing a limitation case. That is that your frequency is very, very high. Therefore, 这个 current 呢几乎都在它表面上头。OK， 电流几乎都在它表面上头，所以我们可以算出它一个表面电流。但是这个表面电流呢是这个电流 per unit length， 所以呢，等于是底下的分布呢我们不理它的细节了，因为全部都放到这里头来了。Okay, but for this calculation, you cannot ignore the details in this direction, because you are calculating R from the circuit theory. You have to have a cross-sectional area. Okay, but the characteristic cross-sectional area is equal to delta y multiplied with the characteristic depth of the electromagnetic wave. OK， 所以这个计算呢是把这里效果全部都把它给归到表面来。这个计算呢是想象它还有一个特定的厚度在那个地方。这个特定厚度呢，这个特性厚度就是 sigma。 所以这两个计算有点不太一样，但是呢，这个它的概念上头呢是一样的。OK，this realistically surface current does not exist. There must be some thickness. 但是 surface current 这个概念创造出来呢，是因为这个方便。在一个量导体里头呢，这个电流就是你就想象就是在一个无限薄的这个范围里头去 ，but in fact it does not exist. Okay, so for this calculation, basically what you calculate for the surface current is the integration of the whole current downward and then lump into a value on the surface. Okay, so think about it. We can discuss a little bit more if you want next time. 所以想想看，然后星期三是我们最后一堂课。我们今天本来有带了一个小考来让你们加分，可是下课了。好，礼拜三我再跟你们见面。